faces. Some of you may remember when I spoke here a year or so ago on cosmology. We're actually going to touch on that on the end. But right now, we're going to talk about the cosmic distance scale. Next chart, please. My trusty assistant will be running the computer. Okay, so I was trying to decide what to call this, but cosmic distance scale is kind of a dry title. How far is that astronomical object in the window? All right, that one went over big. Objects in the telescope mirror may be closer or farther than they appear. Is anybody out there? All right, next try. Thank you, thank you. So I am the Wizard of Stars, but because I saw the movie a few weeks ago, I am not wicked. All right, work with me here. My background is in physics and astronomy. I am a science consultant and advisor to the government. So if anybody wants to hire a consultant, here I am. And I actually dabble in astrophotography here in New Jersey and elsewhere, particularly in Hawaii, which is a whole different world. All right, but we're not going to talk about that today. Next chart. If you have a question, ask the question. Don't wait till the end. You can interrupt me at any time. Despite all the comments, yes, there are stupid questions. I won't repeat any I've heard before. But what the heck? Everybody knows everybody. I'm not taking names. Fire away. And I will at some point probably ask questions of you. They are not trick questions, so don't be thinking, what does he really mean here? What I say is what I mean. Next chart. We'll go into it. Okay, why do we care? I've been asked this question. Why do we care what the cosmic distance scale is? Well, for essentially all of humankind, the ancient people were concerned about survival, and that meant understanding the world around them, and it actually meant understanding what it means for the sun to rise, when the seasons change, when to move from warmer to cooler climates, et cetera, But if you really want to understand the universe and you don't know how far away everything is, you're going to come up with a skewed view of the universe. Really, it's almost innate, even in our day-to-day life, when we look out on a scene, we intuitively recognize this is closer than that. Distance scale is just fundamental to understanding your environment. Next chart, by the way, we will not end up like the dinosaurs, because in December 22nd, 2032, the asteroid's going to miss us. You heard it here first. I was actually working on that a little bit. At the time, it was a 3% probability, which is interesting. It's not like, go crazy, but now it's going to miss us. So at least we have a little time before we get extincted like the dinosaurs. Okay, how do we measure distance? Well, we do this, as I say, in our everyday life. Yes, sir?
Did I read somewhere that it might move instead, possibly?
I don't know if you read it, but yes, it has been written.
Is it true?
Well, who knows what's true in 2032? The probability, I think, I haven't checked this, I think the probability that it will hit the moon is now greater than the probability it will hit the Earth. But it's still pretty low. So, and actually, if it was to hit the Earth, which it will not, it's about the size of a football field. It would have knocked out a city or caused some regional damage depending where it hit. And that would have been a problem. But now, the thinking is, if it were to hit the moon, that would be a scientific bonanza. Right? Because we'd get to see all kinds of response to the moon. Ejecta, seismic signature. So there'd be a lot of science on the moon, but it's probably going to miss the moon. Okay, how do we measure distance? Well, we measure distance on short scales with rulers. When we want to know how far this town was to the next one, we would walk it. We know our step is about that big. We do the math. We figure out how far things are. We bootstrap from there. So there are direct measurement approaches that we're all familiar with. Comparison to an object of known size. Back in the dark days of the drone hysteria, who said he saw a drone, and no question, he saw something. And he said it was the size of a car. And I said, well, how far away was it? He said, well, I have no idea. And I said, well, if you don't know how far it is, how do you know how big it is? And he said, yeah, you got me on that one. So, but comparison to known object size is something we do intuitively in our everyday life. Comparison to known object brightness, classic examples, and this works better out in the country, particularly with a long, straight stretch of highway. I know roughly how bright a headlight is or a street light. If I see another one and it's substantially fainter, I intuitively assume that one's further away. So comparison to a known object brightness is a standard way we use to determine distances. And then another way is distinctive characteristics that we know depend on distance. And we'll talk about that. That is a little bit more removed from our day-to-day non-astronomical lives, but we'll talk about each of these. The systems that get built up for distance measurement are bootstrapped. We measure distances to the closer objects, we determine what that means for something a little further, a little further, a little further. And I'll show you how that has worked over the last 2,500 years for us to understand the scale of the universe. Next chart. Okay, so we're going to start. We can start before this, but it wasn't written. I think going back to Aristarchus of Samos is good enough. He measured the distances of the sun and the moon 2,300 years ago. How did he do it? He made an assumption that that was a right angle. He used a rule that everybody learned in high school geometry and probably nobody remembers today, the law symbol of triangles. And through very simple trigonometry and geometry, you can figure out the relative distances based on the angles. It was pretty good. His accuracy was good enough for 2,000 years, lasted for 2,000 years. That was the gold standard for sun, earth, moon geometry. Now, I'm not saying which one went around the other one. I'm saying just how far they each were one from the other, until the telescope came along and more accuracy started to enter the game. So that's pretty good. If I was well, I am a scientist, but if I was worrying about my legacy, and my legacy lasted 2,300 years, I think I'd check that off as a success. Next chart. If you don't know, if you don't understand, here it is in the original Greek. This is, so feel free to read it. This is actually from a medieval, the medieval scribes and the priests translated or copied the old Greek documents, and that's what that is. And you can see they're talking about the solar system and eclipses and how far things are one from the other. So there it is, and I don't think anyone has an argument of what's on that chart.
Looks good to me.
You say again?
Looks good to me.
Looks. I thought for a moment it might be Latin, but no, I think it is Greek. Next. Okay, let's come a little more towards the current, a couple hundred years forward. Hipparchus, by the way, some of you might have studied this if you took like an astronomy 101 class in college or high school, because this stuff is kind of the beginning point, but I think for most of us that was a while ago. By knowing the distance between two villages in Egypt, and again, geometry and triangles, understanding the distance to the moon. So we're not going to reproduce it, you can Google it, but this issue of how far is this object from us goes back thousands of years. Next chart. Okay, let's move forward, let's move out into the solar system. We talked about the sun, moon, earth, let's talk about the planets. We're now going to jump to the 1500s, 1600s, We're talking about the time of Galileo, the time of Newton, and the time of Kepler. And without going through the mathematical derivation, which you might have seen over the years, you take Newton's law of gravitation, you apply Kepler's observational laws, planetary orbits are ellipses, things of that sort, and Kepler's third law said the period, or the time to go around the sun, squared is proportional to the semi-major axis, or the distance the planet is from the center, cubed. And actually the proportionality is over here, it's proportional to the gravitational constant, the masses of the objects. Kepler and that group of astronomers were very meticulous observational people. They logged everything and came up with these laws. And from this, one was able to establish the scale of the solar system. But we don't care about the solar system. We want to go beyond that. Next chart. But we don't even have to worry about all that gory math, because we're masters of the universe. We could just use our LiDAR ranging system to measure the distance, okay? And you know, in 1969, in the Apollo missions, one of the things they left behind was a laser retroreflector. If you're not familiar with a retroreflector, it's a mirror type device. You shine in from any angle, and the light will bounce back at that angle instead of specular like a regular mirror. And now we can measure the distance between the Earth and the Moon using laser ranging to millimeter accuracy. All right, the Moon is 400,000 kilometers away, and we know that distance to millimeter accuracy. That's pretty good. That's good enough, obviously, that you're not measuring the distance to the Moon, you're measuring the distance to that retroreflector, because that could be in a valley, could be on a hilltop, and obviously that'd be many, many millimeters of difference of range. So that's how we do it today, not just in the solar system, not just to the Moon, but to the planets. We can illuminate a radar essentially to the planets, or now we have spacecraft, we can track them with great accuracy because they're transmitting at us. It's all variation on the same thing. We don't have to worry about that stupid geometry stuff that we all learn that none of us remember. Okay, next chart. Any questions to this point? Taking you through the solar system at fairly accelerated pace. I kind of feel like Captain Kirk. Yes, sir.
Just wondering, do they have to do some correction for the light that travels through our atmosphere?
Oh yeah, oh yeah. So you know, it's like the policeman in a speed trap, right? He's got the radar. He measures your speed and tells how fast you're going. It's a little bit different here. They have to correct for all kinds of effects, and atmospheric propagation is only one of them. Same thing with GPS. You know, your GPS is telling you distance from the satellites, which is then converted to your location. They have to account for the motions of the individual satellites as going around the Earth. They have to account for the propagation of the signal through the atmosphere. They have to compensate for general relativity, relativistic effects. There are a lot of details that I have completely glossed over. But the concept started with trigonometry and triangles, and went now to ranging time. You know the speed of light, you know the distance, because the speed of light depends on whether it's in a vacuum or in the atmosphere. So all those things have to be taken account of. Okay, but that only takes us through the solar system, and okay, so when I was an undergraduate student, I did solar system astrophysics. To me, that was geology. I didn't care about that stuff because I wanted to go to the stars and galaxies, right? Because that's where the action is. So how do we measure the distance to the stars? Well, the first thing to do, and it works for the nearer stars, and this crowd probably knows that the term near compared to solar system distances totally different, right? So the distance to the nearest star is tremendously further than the scale size of the solar system. So we can't do laser ranging, you know, we have to find other ways. And the way we do it is we go back to geometry. And for the nearest stars, we can look at stellar parallax. What is parallax? It's the apparent shift of an object seen against more distant objects if you look at it from two different directions. And in a moment, for those that are not familiar, and you have all seen this, whether you recognized it or not, we're going to do an experiment right here, right now, everybody, and demonstrate that. So actually, let's go to the next chart. We'll come back to this in a moment. So we're going to do the following. Put your thumb over my face. I know that's a painful thing. All right, close one eye and recenter. And then blink your eyes and you'll see your thumb is moving back and forth, right? Did anybody not see that? Okay, that's parallax, okay? So your thumb in this case is a nearby star. And it's close to you. And I'm the background, and the different view angles do not shift me as much. Let's go back one chart.
Back one?
Back one. So there are issues. So we can do this for the nearest stars. But there are not that many because stars are basically far away. And there are issues. How well can you measure that change of angle? Okay? As everybody with a telescope here knows, you're probably doing pretty well if you can get to an arc-second with resolution. And typically, in a place like this, 5 arc-seconds, yeah.
When you did that for the very first time, how did they know which one was the star, the closest one, before they start doing it?
So, how do you know which one's the closest one?
Yeah.
So, at one time, you take an observation of a star field, okay? And then 6 months later, the Earth has gone halfway around the sun, and you take a picture of the same star field. And you'll see most of the stars appear not to have shifted. But some of them have shifted just a little bit, and some just a little bit more. None of them a lot, okay? And so the ones that shifted the most are the closer ones, the ones that shifted medium and medium distance, and the further ones are at some unknown distance, okay? But through geometry again, you can figure out the distance to the nearer object.
How do you account for proper motion too?
Ah, okay. You know too much. So while we're doing this over 6 months, and the reason we do 6 months is that's the biggest baseline we can get from the Earth, right? When we did this was your baseline, a couple of inches. 6 months, we're 2 astronomical units apart. But while all that's happening, the stars have their own peculiar motions, kind of random motions in general. And that can confuse the situation if the star with the proper motion, which proper, for those that don't know the term, it's just the motion of the star through space. And it could be at any angle. It could be towards or away from you, radially. It could be transverse, or more likely, it's some random angle. So this whole back pattern is somewhat moving because of their own individual motion. Now, if they're far enough away, you're not going to be able to see that, unless they happen to be very unusually fast-moving stars. But statistically, you look at enough stars, and you correct for that effect. But it is an effect. And you know, when I say the star is moving, we'll get that in a minute. Peculiar motion is a complicating factor in many of these things. Next chart. Okay. When we talk about, the nearest stars, we could do this out to some number of parsecs. What's a parsec? A parsec is 3¼ light years. What's a light year? It's the distance light travels in 1 year, right? 186,000 miles a second. Works out to about 6 trillion miles a year. Times 3¼ is 1 parsec. Where does the term parsec come from? It's the distance that a nearby star will have a 1 arc-second parallax. So the term parsec is really contraction of parallax of 1 second. Okay, and that works out to 3¼ light years. Now, how many stars are 3¼ light years or closer? None. Right? So obviously, we need to be able to see, to be able to use this approach, we need to be able to resolve better than an arc-second. And you could do a little bit better than that at a professional high-end mountaintop observatory. Or do it from satellites, where you don't have the atmospheric effects, because the atmosphere will blur, as we've all seen through telescopes. And so we can start to push out a little beyond a parsec, but not to many stars. But this forms our basis for the stellar distance scale. Remember at the beginning I said everything's a bootstrap that builds on the previous approach. So this gets us the nearby stuff, of which there isn't much. Next chart, next chart, next chart. We're going forward. Okay, and they say time travel doesn't work. Next chart. Okay, who has heard of Cepheid variables? Okay, well, you're cheating. Okay, so this was the approach that bootstrapped us a big step off of parallax, okay? And now we're going to be, remember we started 300 BC. We're now coming into the 20th century, late 1880s, 90s, and the beginning of the 1900s. Big step. A Cepheid, for those that don't know, is a pulsating star. It's a variable in brightness, and so it gets brighter, it gets dimmer, it gets brighter, it gets dimmer in a very well-defined manner. The star is essentially unstable and pulsing, getting brighter, contracting, getting fainter. But that is we're very lucky to have understood Cepheid variables, because that's what gives us the next bootstrap step. And without that, we would be largely limited to not knowing the distances to distant stars in our Milky Way, much less galaxies, okay? These become useful as what we call standard candles. Standard candle is a meaningful term in astronomy. It means this is an object for which we know with some precision its brightness, its inherent brightness. And next chart. So, in the late 1890s, 1900, 1910, in that rough time frame, Ed Pickering, right there, was the head of Harvard College Observatory, and he had a problem. Harvard College Observatory had all kinds of photographic plates of the sky. This was one of their major contributions, and as a side note, there's like 1 million glass plates of astrophotography, star fields and things. As a side note, that whole archive is in the process. I'm not sure they finished yet, but pretty far along, being digitized. I think by National Science Foundation, provides this amazing archive of what the sky looked like, how bright certain objects were 125 years ago. And that works, that's being used now for research. But good old, he had all these, at Pickering, he had all these plates, and what is the thing, you need somebody to measure the brightness and positions of all these stars on these plates. Well, what, as a manager, what do? You look for cheap labor. And so he had what was called Pickering's harem. These ladies who would work for less than men, who, no political comments, who were amazingly persistent, and in many cases were like the first lady to get an astronomy undergraduate degree at Vassar, something of that sort. They had a connection. They weren't just pulled off the street. Next chart. Nope, go back. So Henrietta Leavitt was one of those ladies. She's in this picture, I don't know which one she is. She discovered that the brightness of these Cepheid variables in the Small Magellanic Cloud, anybody not know what the Small Magellanic Cloud is? Right, galaxy in the southern hemisphere, was dependent on their period. So how bright it was depended on that curve, how frequently, how many days between maximum brightness or minimum brightness was a function of how bright they looked, okay? How did she do that? Just by looking at star after star after star, identifying which were varying over days, weeks, months, and tracking that and plotting it and saying, okay, here's what they are. But then she made an assumption. That's a pretty reasonable assumption. She said, since I'm looking at this cloud of stars, I'm going to assume they're all the same distance. Therefore, if they're fainter, if they look fainter than an adjacent star, they must be further away if they're a Cepheid. I can measure the period because that's easy to do. I just look night after night after night and see where I am on that curve I showed before. And then I can tell which are brighter and which are fainter. Yes?
It's always puzzled me how they could detect the variation of brightness.
Oh, okay.
Before they had instruments.
Yeah. You know what? Hold that question, because I'm going to show you one of these glass plates, and we'll look at that. Okay, so since they're all the same, they must be inherently all the same brightness. Basically, she came up with a relationship that, depending on the period, you can figure out what their inherent brightness was. What's called the absolute luminosity or the absolute magnitude. So these Cepheids became valuable as a standard candle for determining range. That was the big leap forward. Next chart. So here's the actual publication paper. It's, I think, 3 pages. I only took 2 of them. Interesting social thing. In the Small Magellanic Cloud. Now, this was 1912. In 1912, they didn't know what a galaxy was. They knew the Andromeda Galaxy was a nebula. It was called the Andromeda Nebula. They had no idea. They thought all of these, what we now know as galaxies, were clouds of stars in our Milky Way. And our Milky Way was it. That was the universe. Okay? So, hence the use of the word cloud. You'll see the following statement has been prepared by Miss Leavitt. I believe the guy who wrote this paper was at Pickering, because women were not allowed to publish, right? So she did the work, but he gave her credit. And here's the data. And I'm not going to analyze, but notice that the points all fall on a particular curve. Actually, one is for the maximum brightness, one is for the minimum brightness. How do you determine how bright they are? You look at the density on the plate or the size of the stellar image, and you compare it with other stars that you know, and you see this one 3 days ago was different, or, you know, a week ago was different, depending on the period. So, I think, 2 or 3 charts will show one of those. Keep going. So this is today, it's 1995, and you'll see how tight that correlation is between the absolute magnitude or the brightness and the period. Period is very easy to measure, right? You find the time it's at its brightest, you come back next day, you look at it every night, you find out its period is 7 days, okay? You say, okay, 7 days, its absolute magnitude, its inherent brightness is -3.5. I see its 10th magnitude apparent brightness. I can figure out how far it is. I'll show you that in a moment, but it is fundamentally another high school math thing or science thing. It's the 1/r² law for light, right? If I take a light bulb, 100-watt light bulb, and I double the distance, it's now going to be 1/4 as bright. That's what's happening here. Same thing, because in this regard, there's really not much difference between a candle or a light bulb and a star. They're just a point of light. So,
But Jerry, this graph is intrinsic brightness, not apparent brightness.
yes, yes. Now, how did I make that leap from apparent to intrinsic? Because nearby me, meaning in the region of the sun, not in another galaxy, I see Cepheid stars. And from that, I can calibrate that, that relationship. And that's what she did. She said, I see 25 Cepheids. I have this, some of them are close enough I can do parallax. Okay? I now know from parallax how far that particular Cepheid is. I can watch its brightness come and go. And so I know what it's so bright at such and such a distance at such and such a time. And there's a very simple formula, which would be in another chart or two, that connects those. And it's basically the 1/r² law applied to magnitudes.
Is Cepheid another name for pulsar or are they different?
Oh, they're different.
No.
Yeah, pulsar is the remains of a blown up, it's a neutron star. Cepheids are nowhere, they are much younger than that. Yeah, totally different. Why are there 2 lines here? Well, it turns out subsequent analysis since 1912, this is 1995, showed there are actually 2 classes of Cepheids.